really great to be at this workshop, which I think is really at an important intersection of physics and computer science. And in fact, what I'm going to talk about today is this notion of co-designing systems, and in particular, building resource-efficient quantum computing systems, in particular by breaking the abstractions that we typically have for building software systems. Now, the work I'm going to talk about today is primarily from this project called EPIC, which Yunong mentioned, which was generously supported by NSF about 5 years ago, the Expedition in Computing program. And similar to the spirit of this workshop, the team that we have for EPIC is a team of computer scientists and physicists from theorists like Aram Harrow, Peter Shor, and Ike Chong, to device physicists like Dave Schuster and Andrew Houck and Ken Brown, and a whole bunch of computer scientists at University of Chicago. So we started this project about 4.5 years ago with this idea, which is, I think, similar to where we are now, which is we need to get more out of our quantum systems. And in particular, we thought that we could, through co-design, build systems that are 2 to 3 orders more efficient than without this sort of physics-aware approach, systems approach. And if you look at historical progress in hardware development of quantum computers, that's about 10 to 20 years of progress with just hardware development alone. So I think that the subject of this workshop is really important, and is really a great means for us to bring practical quantum computation to reality. Now, it sounds pretty ambitious that we would have a goal of improving things by 2 or 3 orders of magnitude. And in fact, for this workshop, I think going forward even more than that. But in particular, I think that building a domain-specific software stack, much as what has been done recently in classical computing for things like machine learning, is a really powerful approach to getting efficiency from the hardware to your algorithms and applications. And on the left here is just one of the examples I'll show later in the talk of a stack that is very physics aware and goes all the way down to the control pulses of the devices of the machine. And in fact, in the last 4.5 years, EPIC has found many examples of such approaches that we think can really help practical quantum computation. And in fact, many optimizations that if you break abstraction and build software that is physics aware, will give you 2 to 10x better efficiency in terms of, as Yufei mentioned, the resources that you need, the fidelity, the qubits, the number of gates, and sometimes even up to 10,000x if you're looking at the whole design space of different hardware designs and architectures and software systems. And there are just been many of these techniques, which we've published. And in fact, as Yunong mentioned, we did spin out a company called Supertech, which was later acquired by called Quanta. And I won't have too much time to talk about it today, but a large part of our effort, which is part of the NSF mission, as Al Medina mentioned, is to build a workforce and a community in this area of quantum computer systems and sort of at the intersection of physics and computer science. To that end, we published a textbook, have a series of 5 edX courses, and we've also tried to transfer, in addition to our spin-out, our techniques to practice in industry. And so many of the techniques that I'll talk about today have shown up in different industry and academic or sort of government compilers. Okay, so what I'm going to do today is actually run us through a whole bunch of examples And I think I'll get through all of them. Hopefully we'll, we can follow up later after the talk. I'm going through them a little quickly of different optimizations that we can do, sort of walking you through sort of more basic ones that are sort of device and physics aware to more interesting advanced ones. And then I'm going to talk a little bit about benchmarking and how that can affect our field and some work that we've done there. And then I'm going to talk a little bit about moving towards error-corrected systems and some error correction work that we've done. Okay, so let's get started. The first one I'll talk about is, traditionally we have this this notion of quantum gates, which essentially forms the instruction set architecture of the machines that we compile to. And let's just go one step below that and look at, instead of sort of the standard quantum gates, the machine-specific native gates that different machines have. In this particular case, I'm actually going to use an example which was done at our spin-out Supertech for the Berkeley Advanced Quantum Testbed superconducting machine. So the AQT machine was built to be an 8-qubit ring topology. It turns out that 4 of the qubits worked, luckily in a line, so they have a 4-qubit linear machine. Has pretty good gate times and fidelity. And what we're going to do on this particular machine is we're going to take a look at pretty typical algorithm, the QAOA algorithm for max cut, weighted max cut. And we're going to look at a more challenging fully connected graph. And we'll look at how to efficiently map this to the linear topology. It turns out to do that, we use this operation called the ZZ swap. It's this gate that swaps the 2 qubits with the ZZ interaction. And what's interesting about the ZZ swap is that, on the upper left here, you can see the canonical decomposition. But it turns out you can do this more efficiently on the AQT machine if you think about the native gates. So this decomposition on the upper left automatically translates to this set of native gates on the AQT machine on to the right, upper right. But then if you were to use a parameterized control phase gate on the lower left, you get a more efficient decomposition. And then we actually use a simpler version, since at the time they don't have calibrated the parameterized C phase, but with a fixed CS controlled S gate, you get this thing on the lower right. So the first thing that you see is that if you're aware of the native gates that a machine supports, simply you can get a much better decomposition of the operation that you want. But more interestingly, it turns out that there are many, many ways to do this decomposition that are roughly equivalent. So here we can get the same ZZ swap with 3 controlled Zs. And there are actually 32 ways to do this. And then it turns out you can also do it with 2 CZs and a controlled S. And there's 64 ways to do this. And then we have a few commuting rules, so we can do some transformations, which gives you a whole bunch of more different unique ways, these 2 commutation rules. And so what that does is it gives you a whole bunch of different options. And one thing about those options is you can choose the option such that the particular decomposition you insert into your circuit cancels well with the neighboring gates. Okay, so we optimize the schedule so that we can minimize the number of gates we need, because you can actually cancel out some of the gates with where you're inserting this decomposition. But even more interestingly, it turns out you can do this thing, which is a little bit like randomized compiling with no cost, which is we do something called equivalent circuit averaging, where we randomly select decompositions that are equivalent, as long as they don't increase the circuit depth, right? And so what we get there actually is through gate scheduling and this gate cancellation, we get about, for these different two circuits, 30% error reduction, or for a higher depth circuit, it's 7%. And then for this equivalent circuit averaging, we get actually a 60% error reduction, and then a 30% error reduction. So this is really pretty interesting, and I think it's a powerful technique. I think randomization is just a very powerful technique in computer science and also in physical experiments. And in this particular case, we can use the freedom that the compiler has to do an interesting kind of randomization. Okay, so let's take one step further, right? Instead of compiling to the native gates that you've tuned up on a machine, let's compile directly to the control pulses that actually create those gates. In fact, this is Yunong's work for his thesis. And so, here on the left, we have a little piece of a circuit, right? We can think of it as a function that you're computing in your circuit. And on the top right, you see what happens in the sort of a conventional path. You first take that circuit, express it in terms of sort of standard quantum gates, and each of those gates then gets translated to pulses, and you get something that looks like the thing on the upper right. And then it turns out, instead of doing that, we can treat this circuit as an input-output function with a start state and an end state. And then we give it to a gradient descent optimizer, and we just look for the pulse sequence that gets us directly from the start to the end state. And we get a pulse sequence a little bit like the thing on the right, or the lower right. And so it turns out this works great. And the intuition is, if you look at our start state and end state, the conventional way is a little bit indirect, right? We have a whole bunch of gates. The gray arrows sort of go indirectly to where we want to go. And what we're doing here is we're finding a more direct path from the start to end state. It turns out this is about 2 to 10x faster than the conventional way. Now, of course, the problem is, it can compile. It can take hours to actually find the solution. It's an exponentially complex classical computation that we use to try to find these pulse sequences. And this is particularly problematic for iterative computation, right? And in particular, as was mentioned, one of the important algorithms is variational quantum eigensolver, or more generally, variational quantum algorithms, where our quantum hardware, which we might think of as a quantum accelerator, is really providing acceleration for a kernel of a computation. And we have a classical outer loop, which actually computes the full application based upon results from that kernel. And this typically loops thousands or even millions of times, right? And the problem with this is every time we loop, the input parameters change to our hardware, and we'd have to recompile for our pulses. And this is really not going to be practical if it's a million times several hours of compute time. So an interesting observation is, if we look at VQE in particular, we can see that actually most of the circuit is fixed, and only a very small amount of the computation, or just a few gates, change in parameter, and these rotations that are parameterized by an angle that changes each iteration, right? And so what we can do is we can take a very simple classical technique, and we do some sort of partial compilation, and we just fix up the compilation each iteration. Turns out this works great. It's about 10 to 80x faster than the previous method of compiling from scratch. For variational algorithms, this preserves about a 2x speedup. And really, what was exciting here was to break this abstraction of machine instructions and target pulses directly. And you'll see that this was pretty early work in EPIC, and in fact, this has persisted through our efforts that we often use this tool of pulse engineering to enable other optimizations. Okay, So let's break another abstraction. Let's break the abstraction of binary computation, right? So we can look at doing computation with more than 2 levels of logic. And in this particular case, let's start with 3 levels of ternary logic, or Q-trits. So Q-trits are actually, or ternary logic is not a new idea. It was proposed quite some time ago in the classical world. What's interesting is in the classical world, you have essentially a finite amount of signal, right? Let's say between 0 and 1 volt. And you can either divide that up into 2 pieces, or you can divide it up into, say, 3 pieces. But if you divide it up into 3 pieces, you're just squeezing your signal, and you have noise margins. And so you're really making things challenging for yourself. And in particular, ternary logic really just hasn't taken off in the classical world. But in the quantum world, if you look here on the right for a superconducting system, you actually have many energy levels, and we typically just choose the lowest 2 energy levels to represent 0 and 1 for a qubit, and ignore the upper ones. So in some sense, you have more signal that you can use to represent 3 levels. Now, there are some challenges. When you go to higher levels, you have a higher error rate, so you have to be judicious about when you use those higher levels. And in fact, discriminating the different levels is difficult, so measuring 3-level systems to get your result out can be difficult. So in particular, our sort of early solution to this, or proposal, was just to use Q-trits in the middle of your circuit. So it's still qubits in, qubits out. And in particular for something called ancilla, or temporary qubits, to represent some extra space that you need, scratch space. And also to use those Q-trits in at limited times, so that you're not exposing yourself to that extra error in the 3rd level as much. And so it turns out this works great. For circuits that have a lot of ancilla, you can get up to a 70x reduction in the number of devices you need in your circuit on a particular machine, because you're essentially getting more out of each, say, transmon or resonant cavity. And there's a lot of interest from sort of hardware vendors. Here on the right, we show an experiment. We did an early experiment using IBM's Pulse interface to synthesize a 3-state counter on a device. And really, what was exciting about this was, to break this binary abstraction, right? And so this was very promising. We did this a few years ago. And what was interesting was, it turns out, Q-trits are sort of an odd number, literally, and a little bit inconvenient. It was good because it was just the smallest step from binary to another higher level system. But it turns out what we're really interested in is actually Q-quarts, so 4-level systems. And 3-4 years ago, when we looked at this, it just didn't look very good, because the theory predicted that the cost of using Q-quarts and the noise model would make it so that the software and the compiler would not be able to transform circuits reasonably for 4-level systems. And the reason we think it would be a lot more convenient is, Q-quarts would, 2 qubits fit very nicely into a Q-quart. So it gives you some really nice sort of compression of your qubit circuits, and you would get very fast computation internally between 2 qubits that are stored in a Q-quart. So there's some really interesting advantages. But the theory predicts that as you use more and more systems, or more levels, which we would call the radix of your computation, you would get a quadratic scaling, right? And so the quadratic gate time scaling of these operations on, say, Q-quarts made it unattractive. So after doing a lot of pulse engineering in our group, we thought, oh, maybe if a pulse implementation would scale, at least empirically better, right? And so it turns out that's what we did. Here's some work that we did with using Lawrence Livermore's jukebox pulse optimization tool. And here you can see on the left, what's happening is various state transitions from 0 to 1, from 1 to 2, from 2 to 3, and 3 back to 0. And so what you can see is the state populations moving over time using the pulses on the right. And so what we can do is give the software a fidelity target and try to minimize the time and then the decoherence error that comes out of these gates. And what we found was here for a number of different qubit gates, you can look at the scaling of the gate duration, and on the x-axis, we have the radix from qubit to qtrit to qquart all the way up to 8 levels or qops. And you can see that actually it is probably, I mean, the theory would predict it's still quadratic, but it's nearly linear in the region that we care about. In particular, the cost of qquarts is much lower than we might think. And I'm not going to talk about this just yet, but upcoming work shows that, if we use these qquart sort of efficient gates that we've engineered, then we can create a compiler that takes different quantum circuits and compresses them into these qquarts for various qubits, and gives us about a 2x savings in devices with fidelity that's comparable, essentially losing some fidelity because you're in the third and fourth state, but gaining some fidelity because internal qquart operations are higher fidelity and faster. Okay, so those are some examples of things that give us interesting efficiencies by changing our abstractions. Here is an interesting example that I like that has to do with software systems making the job of the hardware easier, or essentially allowing us to build a simpler architecture or system by using software, in this case, to mitigate crosstalk. So in particular, we're looking at this problem where, for example, here on an IBM machine, if you have two parallel operations on two qubit gates on 1 and 2 and 6 and 7, if there's a coupler between them, which you can see 1 and 6 are connected, then the crosstalk can increase the error rate by about 10x. In fact, this is some work from EPIC, also from Prakash Murali from Princeton. And so what we wanted to look at is, could we, in fact, use a tunable qubit architecture to assign frequencies and reduce this crosstalk with the software? And so if we look at the design space of different machines, what we're looking at in this particular case is if we could tune the qubit frequency, but we can't tune the frequency of couplers, fixed couplers between the qubits, how hard would it be to avoid crosstalk? And we can compare this against the IBM machine, which is arguably simpler to build, more manufacturable, but has a fixed qubit frequency at manufacturing time and fixed couplers. And we'll find that, by reducing crosstalk, we get about 13x better fidelity. And then we can compare this against the Google machine, which is, or something that's like the Google machine, which is a tunable qubit, tunable coupler device, which, is built in many ways to avoid crosstalk, because you could essentially turn off the couplers and avoid crosstalk between gates. And but it's arguably harder to build, right? If you look at the evolution of Google machines, we went from something in the sort of 70 qubit range to, after a couple years, to something in a similar range, but with tunable couplers. And that's because, tunable couplers are basically as hard to build as qubits. And so the Google machines are actually sort of 3 times as many qubits as you think, because each qubit is connected to 2 couplers, right? So this is interesting. How do we do it, right? So we do it in 2 steps. One step is to look at the connectivity of the machine in the upper left, and we assign essentially idle frequencies, or the frequencies the qubits sit at. And we do that simply with a 2-color graph, and we just make it so that no 2 neighboring qubits have the same frequencies, right? So no resonance happens between qubits that are just sitting idle. And then we make, in the lower left, something called the crosstalk graph. So this is actually the connectivity of the circuit mapped onto the machine. And you can see on the lower left, this could be quite a complex graph throughout the lifetime of your program or circuit that you're running. But in particular, you only care about the gates that run in parallel, right? So you can break this up into parallel time steps, and each time step only has a very small graph of gates that happen simultaneously. And you can see that in the second crosstalk graph here. And that only takes a pretty easy graph coloring of about 3 colors typically. And that gives us the frequencies that we're going to actually run our gates at, right? And this is important because, of course, graph coloring is a hard problem, and we wouldn't want to have to solve it for the lower left graph here. So if we do this, we can take a look at, on a whole bunch of different circuits, what kind of fidelities we get for these circuits on these hypothetical machines. And you can compare our scheme, which is the red bar, and higher is better, against the blue bar, which is the fixed qubit, fixed coupler like machine, which is sort of IBM-like, which on average is red is about 13x better than blue. And then you can see the green bar, which is the more flexible machine, which is has tunable qubits and tunable couplers, sort of a Google-like machine. And you can see that they're basically equivalent on average. And the key here was to use, this machine-aware software, right? So break the abstraction of perfect qubits and look at crosstalk and schedule the program in a sort of application-specific way onto these machines and make the hardware's job easier. Okay, so let me talk about one of our newest projects that we've done. And let me just back up and say, this workshop is about collaboration between computer scientists and physicists. And I would say that all of our most exciting, best work, I would say, has been in collaboration with experimentalists. And usually it goes something like this, where I'm talking to one of our experimentalist team members, and they say something like, hey, my machine can do this, or I can build this thing. Do you think that would be useful, for the software at a system level? And in this particular case, Andrew Hauk said to me, it would really be a lot more convenient if I didn't have to tune up the same basis gate for every pair of qubits, which typically is a C0 or cross resonance gate. Instead, what I'd really like to do is tune up the best 2-qubit gate that pair of qubits can support, and adjust to the variation in the qubit. And so this led to this fun study we did, which we call let each qubit choose its basis gates. So we're going to let the qubits choose the gates and let the software adjust, right? In particular, this ended up being an exercise in how to choose the best gates. And in particular, you can look at the space of different 2-qubit gates in this thing called the wild chamber, which uses car10 coordinates. And you can see in the wild chamber, you have different gates, identity in the lower left of this tetrahedron, swap gate on the top. And what happens is if you are at identity in the lower right and you move towards the middle of the while chamber, you're basically applying gates that take more and more time. And typically we try to synthesize gates that are on the XX and XY axis, so C0, cross resonance, controlled phase, I swap, or B swap. Those are on these green and red lines. But it turns out that when you fabricate qubits, the frequencies aren't exactly what you think. And what you get when you try to follow one of these trajectories along the red or green line is actually something that's off axis. And you get, here's some experimental plots of what you get when you try to follow the trajectory from an identity towards the middle. And so what you want to do is actually find something on these trajectories that's useful. And in particular, we looked at synthesizing a swap gate, which is really useful on near neighbor connected devices because you're always dominated by swapping and moving qubits around so that you can get them next to each other and perform your computation. And so we're pretty excited because the standard decomposition is the 3 C0 gate, and we thought, oh, well, we can actually synthesize these in 2 gates, and you can see that can be done with these gates on the purple lines, and it also can be done actually with a pair of gates that are different on the blue line and the orange line on the right. Actually, many such instances that are symmetric across the purple lines. But then it turns out we discovered that it takes a long time to support it's a high duration gate to find these gates, or to find gates that are on the trajectory that support these two gate swaps. And so it turns out we found that later that 3 gate swaps are better. And here it's this white region you see in the middle. On the left, we did some numerical simulation and figured out that, oh, it's this volume in the middle of the tetrahedron. And in fact, what you do is you want to look for a trajectory that gets into that middle region. And it turns out you also need to another gate. In this case, we also need a C0 because the C0 is entangling, and it turns out swaps are not entangling. So for our computation, we also need C0 or possibly other gates like a B gate. Okay, so what do? On the upper right, you can actually see that the procedure is to follow the trajectory of a pair of qubits from identity towards the middle. And that trajectory, as I said, is increasing time as you go to the middle. And then as soon as it intersects the plane there, which you can see the red dot is where it intersects the white region in the middle, that's the gate you want, because it's the fastest gate that supports the swap that you want. And then and you can either do that just for swap and then look for a C0, or you can actually find the first gate that can do both swap and C0 in 3 gates for the swap and 2 gates for the C0. Okay. And we have basically these 2 strategies. And if you look at these 2 strategies and you compare it against the baseline, the first one, this criterion 1, where we just optimized for the swap, you can see the swap is considerably faster than the baseline, about 3x faster. And you can see if you sort of try to split the difference between the 2 in the second criterion 2, you can see the swap is still pretty fast, almost as fast as the first one, but the C0 is considerably faster because we try to optimize both at the same time. And the result of this actually is in a sort of decoherence dominated model, we get about an 8x reduction in error in our gates. And if we look at how that stacks up on the critical path of the depth of benchmark circuits, we get about 2 to 30x error reduction on actual applications. There's some challenges. It's going to be harder to calibrate such a diverse gate set. We've taken data on small devices, but we need a larger experimental demonstration of this. But I'll say that it's really exciting to break the abstraction of just sort of a uniform set of basis gates, or sort of our ISA, and allow this sort of heterogeneous set of gates to adapt to the variation of qubits. And I think it'll be a really powerful tool as we go forward. All right, so one more optimization that has to do with technologies and devices. A couple of years ago, we got interested in neutral atom architectures. And in particular, we were interested in the long distance interactions that we get out of these machines. So we wrote a compiler to look at this. And in particular, there were sort of 3 things we needed to look at, right? So we could have longer distance interactions on this 2D array of neutral atoms, but when we have long distance interactions, we can't do things in parallel, right? You get this sort of what we call a restriction zone, where if you have a greater than distance 1 interaction, then you can't do anything else within that zone at the same time. And then we had this other interesting problem that we'll look at the end, which is neutral atoms have this problem called atom loss, which is essentially your qubit can, essentially you lose track of it, and it's not in your array anymore. And so when you run your next iteration or next shot of your circuit, then you don't have that qubit anymore. And so how do we deal with that? And then there's some other interesting things here. Because you have long distance interaction, you can actually do a native 3-qubit operation. And in this case, we looked at how much benefit you get from having a native topology in a single operation. Okay, so when I talk to neutral atom vendors, one of the first questions they tend to ask me is, if we wanted to give you long distance greater than near neighbor interactions, how much distance do you need? And so this was an interesting experiment where we looked at the reduction in depth of circuits by removing swap gates when we have long distance interactions. And what you basically see is a knee in the curve at about distance 3. And so for this set of benchmarks, you can see that about distance 3 is the right thing. And then later we'll see what the benefit is in terms of fidelity of having distance 3, for example, by reducing the depth of the circuit. And then, the other distance, other thing you get is by having native topology. You have about you have these 3-qubit gates that are decomposed typically into 6 2-qubit gates or more, depending upon your scheme. And you can see here that these are for circuits that use a lot of topologies, so an adder and multi-control gate, multi-control topology. And what you find is that combined with interaction distance, you get about, you can get orders of magnitude improvement, right? And here you're comparing the solid line of each color with the dotted line of each color. So what's the sort of the summary here? Well, the interesting thing here is, of course, neutral atoms are relatively newer technology in terms of if you compare to trapped ions and superconducting qubits, and they have some catching up to do in terms of gate fidelities. But what we can do is we can look at a whole bunch of different benchmarks, and what we can do is we can compare the sort of near neighbor no 3-qubit gate version of those benchmarks running on a comparable machine. And that is those are the solid lines. And then the dotted lines are the ones where we add these capabilities. And what you can see here is that if you look at the x-axis, that's the 2-qubit gate error, we assume. And what you see is that the dotted lines, the distance between the dotted lines and the solid lines is actually about an order of magnitude, right? And so you can basically buy yourself an order of magnitude in 2-qubit gate fidelity by having these extra emerging technology features of having longer distance communication and native 3-qubit gates. And then one last interesting thing about neutral atoms is that they have this problem of atom loss, right? And so what's nice is actually the ability to do long distance communication allows you to theoretically skip over a lost atom. And if you have some spare atoms or qubits along the outside of your machine, then you can essentially remap your machine so that it looks like it doesn't have the holes, right? And so this virtual remapping is one way to sort of skip over a hole in the middle here. And then another way would be you swap things around so that if, for example, if the communication distance is too far for the interaction distance you're supporting, you actually have to move qubits around. So if we compare a few approaches, so the best approach is the purple line here. So higher is better because we can tolerate more atoms lost and still support our circuit. If we essentially recompile the circuit onto the machine with by sort of routing around the holes, we can tolerate the most. But it turns out we can very quickly get something pretty close by doing this rerouting, which by itself isn't that great. That's the line that's the smallest. But if we add that to what we call compile small, is basically we compile the circuit a little bit smaller, have a whole bunch of extra qubits, and do this remapping, then we can get quite close to the ideal case of tolerating quite a lot of atoms lost. Okay, so I think the interesting thing here was that here's by looking at techniques to exploit emerging technology, we can see how new capabilities can compensate for maybe gate fidelities that aren't quite as good yet. And we can also see how some of those new capabilities can mitigate disadvantages like atom loss. All right, so that is, I'm at the end of my examples of a few of those kinds of optimizations. But what I wanted to do was take a few minutes to talk about benchmarking. So, we're in this phase where we're trying to improve machines and have co-design of software and machines. So I think it's important to have a notion of what we're trying to improve. And here is a set of benchmarks that we came up with just this year. And in particular, the idea behind designing these benchmarks was to bring sort of a methodology of classical benchmarking and classical computing to the quantum world. And what we did was we tried to find a small set of kernels motivated by real applications. And we wanted them to be scalable, usable on current machines and to future machines that are larger and have better fidelity. And in particular, we came up with something called an application feature vector, which correlates with machine performance. So we try to characterize what was interesting about each of these kernels, and we try to correlate that with how well these kernels did on different physical machines that we ran experiments on. So in particular, we have this thing called the application feature vector. It is an evolving quantity, but it looked at things like the communication the program needed, connectivity, the depth of the circuit, the amount of entanglement, how much measurement it used, how much parallelism it had, what was the liveness of the qubits, how sensitive were they to decoherence. And you can see here for a whole bunch of different circuits that were kernels that included simple state preparation to some simulation and sort of NISQ algorithms to pieces of error correction codes. If we represent these quantities on this like sort of 6-axis circular plot, and then we have a measure of how these applications stress each one of these aspects of a machine, then you can see that the different kernels have interesting different shapes, which we might think of as fingerprints for them. And we also can do things like measure the coverage of these different kernels in this space of features. And then what's interesting is we can take a huge amount of data on all the machines that are out there, and look at how correlated these feature vectors are to the performance or sort of fidelity of these kernels on these machines. And you get this thing on the right, and essentially more purple is more correlated. And in our current set of experiments, what you can see is that in particular for benchmarks such as error correction benchmarks, they're very sensitive to the fidelity of mid-circuit measurement. And what you can see is that the machines that have poor mid-circuit measurement have poor fidelity, which is highly correlated to the fidelity of the benchmark. And you can see those are the purple boxes in this column. And then it turns out that two machines here that had good mid-circuit measurement were essentially insensitive to the mid-circuit measurements, because since they had their mid-circuit measurement was so good, other parts of the feature vector ended up being important. Now, this is definitely a work in progress. I think machines need to become more diverse and more capable for us to gather more data. And we need to sort of come up with different features potentially and better ways of measuring those features on these benchmarks. But I think it's a great start to sort of an evolving effort, which I think will be important to what we're trying to do here. I will just want to say a few words that EPIC and Supertech, now called Quanta, did this work in collaboration. And I think that this is a really interesting model for how academia and industry can collaborate. In particular, the Supermark data that we gathered was much higher quality and many more data points than we would have done if we just did this in our academic effort. We had this sort of industrial strength software called SuperStack, which is a compiler that cross-compiles to all platforms we had access to, and then optimized all those programs and automatically, in fact, executed those programs and gathered the data, and gave us just incredible reach in profiling these different machines and benchmarking them. And this gave us also an avenue to do long-term maintenance and evolution of this benchmark suite in a way that I think an academic group just can't support in a very scalable way. So I think that has been great. And then finally, let me just spend a couple minutes on one last thing. This is some work that we did moving towards the error correction space. And in particular, this is a bit of a co-design between error correction and physical capabilities, physical architecture. And what we did is essentially we looked at trying to build a surface code machine that sort of support the surface code on a sort of greater than 2D conceptual architecture. So in particular, if you look at the upper left, here are 4 surface code tiles, which if you aren't familiar, are 2D structures that as an ensemble encode a logical qubit. There are data qubits, which are black, and the gray ones are ancilla that measure the syndromes between the data qubits. And then here you have 4 of them laid out in a plane. And what we want to do actually is take a different architecture. So let's say on the left, we just have translons. And on the right, we have a plane of translons on the top. And sort of in 3 dimensions, you can think of a 10-qubit memory that is connected to each translon. And that 10-qubit memory in our model is actually implemented with a resonant cavity in different modes of the cavity. And that gives us sort of a 2D plus sort of half D, or I think in classical terminology would call this a 2.5D architecture, which allows us to in fact store those 4 surface code tiles in a stack, sort of in this third or half dimension. So what does that do? Well, there's a trade-off, which is that we have to load one of the tiles up into the translon plane, but then we can interact it with any surface code tile in the stack, right? So that gives us the ability to in fact, have random access to any pair with some cost of load and store of tiles. So what's nice is that stack, that pair of tiles, actually gives us a transversal CNOT, which doesn't happen in the 2D plane. It's 6x faster than traditional methods on a 2D plane. So there's some cost, but we get this compactness and we get some speed advantage. And in fact, we can compact this even more. If the gray ones are ancilla, right, you can actually multiplex the ancilla with the data and smoosh this architecture by a factor of 2. It gives you some serialization in terms of how you load and store and compute upon the tiles, but you can actually use half as many translons this way. And in the end, what we get is a 10x reduction in the number of translons you need and control for the system. And it would give you the ability to build 10 logical qubits on only 11 translons and 9 cavities. And so I think this is pretty cool. It gives these sort of greater than 2D or even just 2D architectures with, say, long-distance communication, give you different capabilities, even when you're looking at the future of error correction codes. All right, so I'm running towards the top of the hour, so let me wrap up. Now, what I've tried to do today is really show you the potential that we have seen in taking this sort of systems view of physical devices and building very optimized, vertically integrated stacks of domain-specific software. And I think that this really has a lot of potential. But we do need to think a little bit about, for the past 5 years, we've really focused on small machines, noisy systems, breaking abstraction and trying to get the most out of machines by increasing the complexity of our software stack. And so there's some cost to that. And the question would be, in the long term, as we get to fault-tolerant, larger machines, how much of what we've learned, where we've specialized so closely to the physics of machines, will be valuable going into the future? And if we compare to classical computation, we're really sort of in the 1950s of classical computation when it comes to quantum machines, right? And back when every bit was valuable at that time, every gate or every operation was valuable at that time. and we wrote very low-level software, and that's what we're doing right now. But I think that as we move into the future, it's hard to predict, but it's hard to imagine that we're going to get to a point where qubits are really free and gates are perfectly reliable. We're going to build error correction on top of that, but I think that the techniques that we have developed for NISQ machines, many of them will generalize to actually supporting error correction circuits, and we also there may be hybrid physical, logical kinds of operations. And I think Misha's even going to talk about analog operations in the future in the next talk. So I think that that what we've learned will be valuable, and I hope that we're going forward, we'll really continue to take this sort of combined sort of computer science physics approach. So in summary, I think we're really at this very historic time, and that we really want to advance this sort of physics-aware computer systems view, both to make quantum computing more viable, but also to develop a workforce of people to make this progress, right? And I talked about a lot of things today. All this stuff is available at the EPIC website, and some of it also, for example, the Supermark Benchmark Suite is available at the SuperTech site. And finally, if you're interested in expanding if you're at a university that's interested in expanding to this computer systems view of things, I have 2 postdocs graduating this year who will be looking for academic positions. And so, I think I hope that that will be an opportunity for this kind of work to grow in our community.